Imagine standing in the moon's shadow as it blots out the sun. Suddenly the world dims, and a pearly white halo shimmers around the black disk. This is the sun's corona, its ghostly crown, a sight that has fascinated humanity for millennia. The corona isn't solid. It's a superheated plasma atmosphere, stretching millions of kilometers into space. Though faint and delicate, it's a region of immense power, where the solar wind is born and magnetic fields rule. For most of history, the corona was a fleeting vision, visible only during total solar eclipses. Early astronomers even debated whether it belonged to the sun or the moon. Today we know it's a dynamic, ever-changing part of the sun, sometimes smooth and symmetrical, other times spiky and wild. The light from the corona tells a complex story, a mix of sunlight scattered by dust and the glow of superheated plasma, its temperature, density, and chemistry. The corona is an atmosphere larger than the sun itself, a shimmering extension of our star's influence. Its ever-shifting form hints at powerful forces we're only beginning to understand. Studying the corona is like cosmic archaeology, using light to uncover the physics of a place we can never visit. It's a reminder that even our familiar sun holds mysteries waiting to be revealed. The corona presents one of astrophysics' greatest puzzles, the coronal heating problem. As you move outward from the sun's core, temperatures drop until you reach the corona, where they skyrocket to over 1,000,000 degrees Celsius. It's as if you walked away from a bonfire and got hotter, not colder. The sun's surface is about 5,500 degrees Celsius, but the corona is hundreds of times hotter. This defies basic thermodynamics. How can the outer atmosphere be so much hotter than the surface below? The mystery deepened in the 19th century, when astronomers found strange spectral lines in the corona's light. They thought they'd discovered a new element, coronium, but in the 1940s, physicist Bengt Edlund revealed it was actually iron, stripped of electrons by extreme heat. The real question became, where does all this energy come from? The sun's surface is a turbulent sea of hot gas, but how does that energy leap into the thin outer corona? It's like trying to heat a cathedral with a single candle. The process must be incredibly efficient. For decades, scientists searched for the mechanism that could pump so much energy into such a vast, sparse region. The answer must lie in how the sun's churning surface transfers energy upward. The corona's million-degree heat remains one of the sun's most enduring mysteries. Solving it could unlock secrets about stars across the universe. The quest continues, driving new discoveries and missions. To solve the corona's heat puzzle, scientists turn to the sun's magnetic fields. The sun is a magnetic powerhouse, with field lines channeling energy from its surface into the corona. One leading theory involves magnetic waves, Alfvén waves, generated by the sun's turbulent surface. These waves travel along magnetic field lines, crashing and releasing energy that heats the corona. Spacecraft have now detected these waves, confirming they carry enough energy to matter. Another theory centers on nanoflares, tiny magnetic explosions proposed by Eugene Parker. Billions of these nanoflares may erupt every second, each releasing a burst of energy through magnetic reconnection. Recent images show tangled magnetic structures that support this idea. It's likely both waves and nanoflares contribute to the corona's heat. The sun's atmosphere is a cauldron of invisible forces, with energy delivered in ways we're only beginning to grasp. The answer may be a combination of these processes, each playing a vital role. To truly understand the corona, we had to go there. In 2018, NASA launched the Parker Solar Probe, designed to fly closer to the sun than any spacecraft before. Protected by a revolutionary heat shield, Parker entered the sun's atmosphere in 2021, crossing the Alfvén surface. The probe now samples the corona directly, measuring particles, magnetic fields, and waves. One major discovery: switchbacks, sudden flips in the magnetic field carrying huge amounts of energy. These structures may be key to how the solar wind accelerates and how the corona is heated. Parker's data is transforming our understanding, testing theories with real measurements. The mission is a testament to human curiosity and our drive to explore the unknown. The corona is a complex tapestry woven from magnetic fields. Colossal coronal loops, arches of glowing plasma, trace magnetic field lines connecting regions of opposite polarity. These loops, stretching hundreds of thousands of kilometers, are the building blocks of the lower corona. They're dynamic, constantly shifting and glowing with superheated gas. In contrast, coronal holes are vast, dark regions where magnetic fields open into space, letting the fast solar wind escape. Helmet streamers, enormous, pointed structures, form over boundaries between open and closed fields, often visible during eclipses. Streamers are the source of the slow solar wind, while coronal holes feed the fast wind. Together, loops, holes, and streamers reveal the sun's magnetic influence in action. The corona's structure is a living map of the sun's ever-changing magnetism. Studying these features helps us understand how energy and matter flow through the sun's atmosphere. The sun's magnetic tapestry is both beautiful and essential to life in our solar system. The corona is also the stage for the solar system's most violent explosions. When magnetic fields in active regions snap and reconnect, they unleash solar flares, brilliant flashes of energy. A large flare can release the energy of billions of nuclear bombs, heating plasma to tens of millions of degrees. These flares can disrupt radio communications and affect technology on Earth within minutes. Sometimes flares are followed by coronal mass ejections, giant clouds of plasma hurled into space. If a CME hits Earth, it can trigger geomagnetic storms, causing auroras but also threatening power grids and satellites. Understanding the corona is vital for predicting space weather and protecting our technology. The sun's temper can be both beautiful and dangerous. Studying these eruptions helps us prepare for their impact on our world. Humanity's fascination with the corona spans centuries. For most of history, it was glimpsed only during total solar eclipses. In the 18th and 19th centuries, astronomers identified the corona as a true solar feature and gave it its name. The invention of the coronagraph in the 1930s allowed continuous study, simulating eclipses with an occulting disk. This revolutionized solar physics, revealing the corona's structure and activity. The space age brought telescopes above Earth's atmosphere, letting us see the sun in ultraviolet and X-rays. Missions like SOHO and SDO have mapped the corona's magnetic fields and eruptions in stunning detail. Our evolving technology has driven each leap in understanding, turning fleeting glimpses into continuous discovery. Our sun isn't unique. Many stars have hot, extended coronae. Stars like the sun, with turbulent convection zones, generate magnetic fields that heat their outer atmospheres. Young, fast-rotating stars have even more powerful coronae, glowing fiercely in X-rays. Their coronal temperatures can reach up to 40 million degrees Celsius. In contrast, massive blue stars and Type A stars lack coronae, missing the magnetic dynamo needed. The presence or absence of a corona reveals a star's inner workings. Studying other stars' coronae puts our sun in context, showing the range of stellar activity. By comparing thousands of stars, we refine our theories of coronal heating. Are nanoflares and alpha waves universal? The answers help us understand stars and our own sun more deeply. The sun's corona is just one example in a universe full of stellar mysteries. Studying the corona isn't just about solving a physics puzzle. It's about understanding our place in the cosmos. The corona shapes the solar wind, influencing every planet in the solar system. Our technology is vulnerable to the sun's outbursts, making space weather forecasting essential. The corona's activity can even affect the habitability of planets around other stars. By learning how coronae work, we protect our world and search for life elsewhere. The sun's stable corona may be why life thrives on Earth. Ultimately, we study the corona because it's mysterious, beautiful, and fundamental to our existence. The quest to understand it drives us to explore, discover, and wonder about our place among the stars.